Let's do it to it, people. Third assignment. We're talking moment of inertia here. So I would strongly encourage you guys to go and if you still have questions or confused by moment of inertia, go look at the Zoom meeting from Tuesday that I posted on Google Classroom. Talked a lot about that with the three people who were attending the meeting, including some like visual representations with the sledgehammer that I had in my garage. Um, but moment of inertia, again, is an analog. It's the rotational analog to mass, right? Mass is the equivalent of inertia. And remember that mass or inertia can be best described as um, being a resistance to acceleration. So then rotational inertia, or what we would call the moment of inertia, is basically the rotational mass analog. And it would be the resistance to rotational acceleration. Basically, how difficult it is in order to rotate or cause that object to change its rotation, rotationally accelerate. And it's denoted with a capital I. And that is proportional to or affected by two things. Thing number one is the overall mass. Of the object. So, it's obviously if you have like a very light, I don't know, like stick or twig, it's very easy to rotate that to cause it to rotationally accelerate because it's very light, right? If you have a lead pipe of the same dimensions, it'll be more difficult to rotate that lead pipe simply because the lead pipe has more mass and therefore more inertia in general. The second thing that affects this, though, is where the mass is relative to the pivot point or the point of rotation. And that's what we call R. Traditionally, for rotational inertia, moment of inertia, mass and R are represented with capital M and capital R for some reason, um, maybe to differentiate them in a rotational context. So here, uh, because we have all of these different, we need to consider the overall mass of the object, and we need to consider the mass distribution relative to that pivot point. So different objects will have different distributions of mass relative to the pivot point. So for example, if I have a mass of m, and all of that mass is located at a distance of r, right? Now I have like 100% of mass is at distance r. So that obviously has mass m, but it's very far away from the pivot point relative to, say, a uniform rod that still has mass m, but that mass is closer to the pivot point now. Since it's closer to the pivot point, it'll have a different uh, radius of mass to pivot, right? So different shapes, different sort of mass distributions around the rotation of the axis of rotation will have different formulas for moment of inertia. The sort of base formula for all of these, the base formula for I is the integral of, uh, sorry, the integral of the distance squared with respect to the mass of the object. So basically, I mean, like the long and the short of it is, in the history of the AP exam, anytime moment of inertia has come up, they've uh, given you the formula or asked you how to derive the formula. If they give you the formula, you just use the formula. If they ask you how to derive the formula, then you would write this equation and move on. It's really not worth the time that you would spend trying to get the one extra point for solving this integral, right? So in the event that they ask you to calculate a moment of inertia, which is again unlikely on this particular exam, I would encourage you to just write this integral formula and move on. That'd probably be the best use of your time for maximizing points, especially given that the College Board just said that they intend to write this test with more questions than you have time to answer. So you're definitely going to be leaving some blank. Um, that being said, the exam itself will be open book, open note. And so if they do ask uh, a rotational inertia question and they don't give you the formula already, but they give you the type of object. So, for example, they say it's a solid cylinder rotating around a central axis. I would encourage you guys to print out or bookmark this table so that which I'll share on Classroom, so that you have quick access to these different formulas. So, maybe the question says, oh, hey, it's a solid cylinder rotating around its central axis. So all you have to do is pull up the table, find solid cylinder around central axis, and it gives you the equation that you would use for the rotational inertia, right? So that would be my recommendation for you guys. Going back to these questions, we have a rectangular sheet of plywood attached to a vertical support by a set of hinges. So we're given the fact that the sheet is uniform. We have a height, a width, and a mass. So you can sort of think of this as, a door frame, and this is going to be my pivot point. And then attached to the door, we have this swinging sheet of plywood. So my R here is going to be the length of this door. That would be the width. So R equals the width. Mass obviously equals the mass. And hey, look, that's all we need to use any of these formulas, right? These formulas are only dependent on uh, the mass and the distance of that mass to the point of the rotation. And so um, to answer question B right now, the height of the sheet is unnecessary, right? The height has no bearing on this because height, how tall the door is, doesn't affect the relative position of the mass to the pivot point. So that's easy then. And if I'm thinking about this door is basically just a really thick, can be modeled as a thick uh, solid rod, right? I mean, it's solid all the way through and uniform. So that's our solid. And then it's just a length, and it happens to be a thick rod, but it's a rod nonetheless. And so we could model this using a rod about the axis through the end perpendicular to the length. So my moment of inertia here will be 1/3 ml squared. So going back here, I would use I equals 1/3 ml squared, where L here is the width, and plug in and chug out. Now, going to the second question, um, I'm imagining that I'm standing tall and turning about a vertical axis that passes right through my head, down in between my, right through the center of my body, right? And we're asked to compute an order of magnitude estimate for the moment of inertia. So it's saying solve for I. Just to clarify, order of magnitude means to the nearest power of 10. And so obviously your mass is going to vary, and your shoulder width is going to vary, but it doesn't really matter for this question because we're approximating it to the nearest factor of 10. And so if you're off by, you know, 10 centimeters, uh, it's not going to make a difference in the long run. So the real question here is, what shape is my body best modeled as? And the best answer to that is probably a relatively solid cylinder, right? So I'm sort of like in this case, uh, I am a solid cylinder rotating about a central axis. And so I would use 1/2 mr squared for my moment of inertia here. Again, approximating my mass and approximating what would effectively be the radius of my body, or from, like, say, the very center of my chest to the very outside of my shoulder. And then I would plug those numbers in to my moment of inertia equation. So I would model as a solid cylinder and use I equals 1/2 mr squared, approximating m and r and plugging them in. Basically, then you're just rounding, right? So there's an example given here. Obviously, your specific numbers may vary. If you're, say, a very large person, then your mass is probably more than 60 kilograms. It's about, what, 135 pounds or something like that. But, it's a good approximation. So then lastly, this last problem is an example of uh, a problem where uh, you are asked to find a proof of the moment of inertia for a situation. So here we have a solid rod that's rotating around a central axis. Looking at my table, I already know that a solid rod rotating around a central axis, um, sorry, it's the end of a rigid rod. So we're not rotating around a central axis here. We're rotating around the edge of the rod. So I already know that my formula here is going to be 1/3 ml squared. This question is basically asking you, how do you get there, right? And so we set up the integral of this scenario where I is going to be the integral of r squared dm. And again, they work out the solution down below, but um, like, my recommendation again would be for a question like this, that if it's asking you to solve for a moment of inertia, you know that you're going to be using this integral, start there, and then it's probably not worth the time for the rest of the points in the problem. Most of the time, in the 3 or 4 questions that have shown up in the history of the AP Physics C exam, it's a 2-point question. 1 point is just writing the integral, and the other point is solving the integral. Writing the integral takes a matter of seconds, and solving the integral could take upwards of minutes. I really don't think that that type of question is going to show up on this year's exam. If it does, that's my suggestion. So, yeah, that's it for Moment of Inertia. And I'll catch you guys hopefully at our review session on Thursday for our office hours. Yay! Bye.